All right, we've got our last two questions here with some interesting formatting. Um, but here we go, let's dive in. So this says f plus g of -3, and you can see we've got two different graphs here. F is graphed in blue, g is graphed in red, but they want f plus g of -3. Now, here is, again, the big idea, and here's what we have this thing called the vertical line test, is let's put our vertical line at -3. There it is. Here's what I now know. I now know that f at -3 is 3 because that's on my vertical line. That's how high I was, 3. What about g of -3? G of -3 on that vertical line is -1. So great, I now know what f and what g are at -3. They're 3 and -1 respectively. And so guess what? All I need to do, according to this, I know this looks like we're multiplying here, but we're not. It's actually, well, there is multiplying or distributing, but it's this. It's that they want f of -3 plus g of -3. Catch that. The -3 is distributing to f and to g, and so there's no multiplying happening anymore. It's the addition of two functions. And I know what you're asking is, Mr. Rao, why would they write it like this and not like this? Because they didn't want to write -3 twice, because mathematicians are lazy, as I've said. So if writing it like this saves them from writing -3 a second time, they'll make you learn that, hey, this isn't really multiplication, it's just add those two results. Well, I've got my two results. If I add them, I get 2. And I'm done. Then we get to this one. Well, first we have g of f of -2. And once again, this is one of those compositions where there's an actual value. So we're going to read this from right to left. So -2, well, I just said -2. Let's draw my vertical line here. Now watch this and be careful. I need f of -2 first. So on this vertical line, careful, f is the blue graph. On my vertical line through -2, careful that you're counting that right or seeing that right visually. It looks like f of -2 is 6, is how far I go. Now watch this. Function composition then says I wanted g of f of -2, but you just figured out that that is 6. All right. So hopefully again you catch that we wanted g of f of -2, but since f of -2 is 6, I'm really saying I just want to know what g of 6 is. Well, now that I say I want g of 6, guess what I now need? This is kind of interesting. I need another vertical line. And this, we're really doing some crazy math here. This is really kind of the heart of algebra, plugging functions into one another, doing functions in more than one step. So follow this argument. We need a -2. There's my first vertical line. -2 on the vertical line for f got me 6. 6 on to g now takes me to -9. And that's your final answer. So, if we could say it another way, -2 through f is 6, and consequently 6 through g is -9. Catch that logic and that flow there, and that finishes up 2.6. Now we have 2.7. Um, so the idea is we need to talk about inverse functions. Well, an inverse function is a special thing. It's really, well, actually, let's just define it. We'll say if f and g are inverse, then both must hold. And what do we mean by both? Well, here we go. It means that f of g of x, so composition isn't going away, should result in just x, and plugging it in the opposite order should also give you just x. And now we're saying if this is true, catch this, we're going to get a new symbol here. G of x is equal to f inverse of x is how we write it. So that f to the power of -1 is the way we would literally write it, but what it means is f inverse of x. And finally, now we get to one-to-one. That's one quick definition. It's that, we'll say it like this. A function passes the vertical line test. Well, number one, it had to, because if it didn't pass the vertical line test, it wasn't a function in the first place. But also, and the horizontal line test. So in other words, you try the same idea. Can I draw a horizontal line and it only touches my graph at most once? If you can, then you found a function that's one-to-one. And all I want to say about one-to-one is this. It's a function that is invertible on the entire domain. Interesting. That's very abstract, and we don't need to say anything more than that, so we won't. Let's dive in to do some examples. You can see we're almost done, just four, but we've got to do 2 compositions per problem. So here we go. We first need f of g of x. All right, let's get our skeleton going, as I call it. Here's the skeleton of f. F takes what you plug in and multiplies an 8 and then adds a 4. I'm just writing it with parentheses. And now we will compose that, or fill that, with g of x. Now g of x is on the left, but on the right, it's this actual algebra. Now this is where you need to be careful, but watch this, or let's say it like this, or hear it like this. If all of x minus 4 is being divided by 8, and then I'm going to take that result and multiply it by 8, then guess what? These two cancel, and this is x minus 4 plus 4, and guess what? That's just x. Cool. Now, 9 times out of 10 in this class, if you got, really, I'm going to say 999 times out of 1,000, when you compose these and you just get x, you're going to get x again. So I'm not saying don't do the work, but I am saying if you got x the first time, you should feel pretty confident you'll get it the second time. But let's prove it to ourselves and then show that these are inverses. Up next, for g, the skeleton of g looks a little bit different. It looks like that. So g says I'll take what you want, subtract 4, and then divide all of that by 8. So I wrote the skeleton. All right, let's compose or fill the skeleton with f. There we go. Let me just get a little more space. That looked too close. All right, so there's my first step, and now let's work this out. The parentheses are no longer needed, and so in order, what would then happen is you would have some 4's cancel, right? Since the parentheses aren't necessary, since there's no exponent or nothing to distribute out front, there's going to be an 8x and a plus 4 minus 4. Well, the plus 4 minus 4 is just canceled. And now you have 8x over 8, and guess what? Those 8's just canceled. And so they are inverse, is the short answer. So great, we just found two functions that are inverse of one another. Now let's look at number 2. For number 2, copy the skeleton of f. There it is. And now let's compose or fill that skeleton with g of x. G of x is what's written on the left of the equal sign. And x plus 5 over 4 is what's written on the right of the equal sign. Kind of changed the way I wrote how I composed it, but that is correct. So there we go. Now let's work this out though and think carefully. Do these 5 and 4's cancel kind of like they did up here? The short answer is no. Now your homework is not going to let you get away with just simply writing this out. They want a final quote unquote simplified answer. And so what we're going to do is take the 5 and distribute it. That would be 20x, sorry, not 20x. I was thinking ahead. That's going to be, maybe I'll even write it like this. Yeah, that's going to be 5x plus 25 over 4 minus 4. I know that feels like we're done. Again, we distributed careful. This is really 5 over 1, right? That's a whole number 5, so it's really over 1. So only the 5 distributed up top. It was still just 1 times 4 on the bottom. Now this even looks like we're done, but we're not, your homework would argue, because there's two different things here. Can we write one fraction? The short answer is we can if we do this. If we make common denominators. If I multiply this by 4 over 4, I get negative 16 over 4. Again, stop, pause, think right there. Negative 4 and negative 16 over 4 are equivalent, but now they have a common denominator. And so now I can finally write that f of g of x is, goodness, 5x plus 9 all over 4. So I can actually answer right away, are they inverse? No. So I'm done there, and I found f of g of x and saw that that clearly wasn't just x by itself. So guess what? When you compose it in the other direction, it's also not going to make just a simple x, because if it didn't work for the first composition, it's not going to work for the second. And I'm going to skip it for sake of time, but you would still in your homework need to copy the shell of g and plug f into it as well and see what you get on that end as well. Just be aware of that. All right, let's go through our last two, and then we've got a graph, two graphs on the back. So we have f that needs to be composed. This is the skeleton of f, that inside a square root, whatever you plug in will be subtracted by 8, and then, sorry, not square rooted, but cube rooted after the fact. All right, well, let's fill that in. There we go. I plugged in g of x, but g of x is x cubed plus 8. Now, careful about the order of operations here. From there, here's what happens. The parentheses are unnecessary because inside of this cube root, there's nothing multiplying first to that parentheses. There's no exponent inside on top of the parentheses, so the parentheses aren't necessary. And I'm going to go ahead and say that then guess what happens? What happens is the positive 8 and negative 8 cancel because the parentheses don't need to be written anymore. From there, I'm cube rooting something that's being cubed, and guess what? Those literally are what we would call as mathematicians inverse operations, so you bet they cancel themselves out, and I just got x. And so I'm now pretty sure these are inverses, but let's verify. There's now g, and g is something cubed plus 8. Well, g needs to be evaluated with, or be composed with, f, and f is big cube root x minus 8. That parentheses where we evaluated or substituted or composed was cubed after the fact, and then 8 was added after that. So great. I've now composed, I've plugged f into the shell of G. Now watch this. Now, according to order of operations, we should cube root everything first and then cube. But guess what? Those are, again, like I said, by definition, inverse operations. And so right off the bat, the cubing of a cube root cancels, and 8 minus 8, or negative 8 plus 8, cancels, and I just got x. So these indeed are inverse. All right. We've got one more to kind of go through here, and then just some quick pictures on the back. I want to show you the way your homework is going to format this. Now, it says given f is 1 to 1, show its inverse and find its inverse. So, in other words, what they're saying is this function is invertible, and we can find its inverse. The question is, how do I do that? See, before we were given two functions, we were asked to show their inverse. This time they're saying this one can be inverted. What is its inverse? Here's the short answer of what you do. It's kind of a quick four-step process. Instead of writing f of x, you write y instead, because that just looks a little more normal. Now watch this, all right? That's step one. Just write it as y. Here's step two, and this is the big one. Switch x and y. Now when you switch x and y, you now have x equals 7y plus 3. Step 3 is solve for the, I'm going to put it in quotes, new y. All right, so catch those steps. First, just take your function, and instead of writing the fancy mathematician f of x, write y instead. After you've written y instead, switch everywhere you saw an x, write a y instead. Everywhere you saw a y, write an x instead. Switch them. And then now solve for y. All right, well, here we go. Step 3 we're going to do over here. To solve for y, I would first, let's think about this in terms of PEMDAS. 7 and y are one term. There's this other term 3, so according to order of operations, we would first subtract that 3 over to help get y by itself. Now all I need to do is divide 7, and as I do that, I'm going to reorder it to put that on the left. Careful, all of that's over 7. And so there's step 3, and step 4 is right with, I'm going to write symbol. What do I mean by that? Well, this is no longer just any old function. This is f inverse of x, and that's x minus 3 over 7. Now, what we're not going to do ourselves is we're not going to actually show the work of verifying it. But the idea is when they say that, what they're saying is, could you then take, maybe I'll just write out what the first step would be, 7x plus 3, and plug in, right, 7x plus 3, the original f, and plug in what I just got and show that it cancels to x, and hopefully you can even see, yeah, the 7's canceled, then the 3's cancel, so we're done. But catch this, what, excuse me, what did I just do? I just took f, and then I composed it with, and it looks ugly at first, its own inverse. Goodness. Or to write it this way, that is f of f inverse of, whoops, x. And that, again, that looks nasty in the way that they write that out with the symbols, because it's really subtle where that little inverse is, that little to the power of -1 is, so to speak. But it is there, so just catch that. That's what you're doing. You're composing f with itself when you read that homework example. All right, two more and they go by super, super quickly. So the question is, Do these graphs pass the vertical line test? Yes, they do. Do they pass the horizontal line test? This one does, so it's invertible. This one doesn't. Interesting. So this function is not one-to-one. It doesn't have an inverse across the entire domain. What would its inverse be? Well, we'll encounter some of that in later chapters. But that's the end of Module 4. I know there was a lot packed into this one this week, and hopefully it gets easier to compose those functions over time. I think my biggest piece of advice is don't skip the step of writing the shell and then filling it. That makes it so much easier. And just think, if we didn't write that first step and we just started showing all this work right here, that'd be pretty confusing to look back later and just see everything already plugged in and stuff already starting to cancel. Write the shell, then fill it in. Awesome. Well, have a great week and let me know if you need anything through email, and I'll digitally see you, or you'll see these videos or more of them next week. Bye.